All right. Welcome everyone to the webinar today. I'm so happy to have two very fine guests today with Henk Boden and Marco van den Brand. And we are going to talk about trying to do thermal remediation at sites where the groundwater is flowing relatively fast. What do we do about that? Before we introduce the two panelists, I just want to give you a little bit of background. In the world of geology, of course, you have formations that are super tight with no water flow at all, fractured rock or rock without fractures. You can kind of rank it from very, very low permeability to high permeability. Gravel has a lot of water flow if there's a gradient, sand, silt, clay. So in terms of permeability, you can have it on a range like this. You can also estimate how fast water flows in different formations depending on the gradient. If you have the same gradient, let's say it's 1%, that the water table has a gradient of 1, roughly these are flow velocities. So in some sites, it can flow as much as, this is 30 meters per day. You can imagine how much water that is. Can run across a football field in 2 days, the water. That's how fast it can move if you have a gravelly aquifer. Other sites that are more typical with sand, maybe the water is moving 1 meter in a week or something like that. So you can imagine if you're trying to heat a site to the boiling point of water, for instance, it matters whether water can move across the site in 1 day or 1 month or 1 year or not at all, because as that water does so, it will cool or move water or heat from the zone. And with that in mind, we use different thermal technologies. You can kind of see them here for the high permeability zones where water is moving very readily. Steam can be injected, and steam enhanced extraction is typically a favorable solution for that. If you have very tight material and there's not much water, thermal conduction heating has been used very effectively in crystalline rock, for instance, and also when there is some water flow. In between those two kind of extremes, there is electrical resistance heating, which can also heat. As long as there's water, you can get heat, and you can accept a little more water flow and still get enough power in, because when it's nice and wet, it's also easy to inject electrical energy. So we pick the thermal solutions based on the site conditions. Sometimes we combine them. Sometimes we have ERH in the top or TCH at the top and steam at the bottom. Just depends on the layering. So what would happen if you forgot about this? If you have a site, this is illustrating temperature. If it's red, it's 100 degrees. It's nice. It's how it's supposed to be. If you have very low flow velocity of water, maybe 1 gallon per minute, you don't have a problem. If you have maybe 5 or 10, what happens is you, on the up gradient side where the water flows in, you get cooling. And on the down gradient side, if you don't extract enough liquid, you lose contaminated warm water on the downside. So that is unacceptable, right? You don't want to create a problem down gradient, and you don't want to have an area here that's not treated properly. So what are your options? Of course, you can choose the best thermal technology. If you're trying just to stop the water, you can use a barrier such as a sheet pile wall or a slurry wall, or you can pump water out so that it doesn't run across, and then you can re-inject it or treat it, or both. You can also use steam, as I explained before. What we'll hear about today is an electrical resistance heating application where the water was known to flow very fast, and where Marco and Henk dealt with that issue in a quite different way than you're used to, but they combined remedies. So before we get into that, I would love to ask Henk and Marco, first Henk, to introduce yourself. Tell us a little bit about you and your company and how you got involved in this piece.
Yes, thank you, Gorm, and good morning, good afternoon to all. My name is Henk Boden. I work for Kaldek in the Netherlands. Kaldek is a worldwide producer and distributor of chemicals and food ingredients, around 14, 15 of the world. And in our company, I'm responsible for remediation projects as our company has been in the chemical world. Well, as many companies, we have some sites where we have some pollutions. Thank you.
And Marco?
Yes, I'm Marco van der Brand. I'm Managing Director of HVT and also for ERH Europe. And HVT is an in-situ remediation expert company, so to say, based in the Netherlands as well as in Belgium. But we do projects all over Europe and all kind of in-situ remediation technologies, the classical ones, but of course also with ERH Europe in-situ thermal remediation. And myself, I work now for over 25 years in the in-situ remediation business.
Very good, thank you. And Henk, if I may start by asking you about the site, where is it located and what happened at the site that we're going to talk about, please?
Yes, of course. The site we're talking about is located in France, as you can see on the slide, in the very beautiful town Barberet-Saint-Sulpice, as it's called. Caldic acquired a number of sites in France, and this site was one of them. At that time, it was already closed, so there were no activities anymore. But well, it was part of the deal: take it or leave it. We were aware of some contamination on site, but we had no choice. We had to accept it, and by that also well aware that we had to do remediation on site.
Okay. Next time you speak, Henk, maybe if you can have the microphone a little bit closer. It was a little bit difficult to hear you, but I could hear most of it. So
okay.
Yeah. Marco, would you mind explaining a little bit about the site, the conceptual model, and so on, please?
Yes, I'll do my best, Gorm. Sorry for my Dutch accent here in the English. I hope I do well. So as you can see, as Henk explained, the site is located in the north of France in the Champagne region. But as you can see on the picture on the left, maybe Gorm, you can pinpoint it. It's the red spot over there. That's where the site is located, close to the little village of Barbery and close to the city of Troyes. The site is also very close to the river Seine, which eventually runs into Paris. And the groundwater is, let's say, flowing downhill in the valley of the river, and also passing the Caldic site. And as such, the pollution that was present at the site of Caldic was also flowing towards the river of the Seine. If you look at the subsurface, it's I would say the first, let's say, 5 meters is clay tilt, I think you say in English.
Mm-hmm.
And then below 5 meters, it's getting more and more chalk. And then, you know, it becomes like, if you look at or think of the White Cliffs of Dover, that kind of stuff, so to say. So clay on top and chalk more in the deeper treatment zone. Mm-hmm. The water flow was about 10 meters a day, especially in the deeper layers of the treatment zone. So very, very fast flowing, as you could have nicely explained, Gorm.
So,
yeah.
So if you treat a site and it takes, let's say, 4 months, 120 days, it could run more than a kilometer. The water can move more than a kilometer. So that's pretty obvious that if we don't do something about that, the site will probably never get hot, no matter how much power you put in the ground, right?
Sure. Yeah. So we investigated very thoroughly how to prevent hot water flowing away, so to say. Yeah.
We forgot to tell anyone what was the contamination at the site.
Sorry, that was my fault. Yes, the site was polluted very heavily with chlorinated solvents. As you can see here also in the picture, estimated to be 6.5 tons of fluorinated solvents, and especially mainly PCE. As I said, on the site itself, there was a real hotspot with DNAPL. The pollution was present from groundwater level, which was about 4.5 meters below surface, towards circa 12-15 meters below surface.
Yeah.
And the total treatment volume we treated eventually was about 9,000 cube. As you can, perhaps, I don't know if people can see, but soil concentrations, maximum concentrations went up to 1,500 milligram per kilogram dry rate.
In here, yeah.
Yeah, so
That's obviously DNAPL present for if it's PCE and you have that much, there is DNAPL in the soil. Yeah.
yes, correct.
So it's a real source area. Yeah. Henk, would you mind telling us about the treatment objectives? While you do that, we can show a plume, show the dissolved plume, right?
Yes, and of course here on the picture you see already our big concern. The plume was under the village, under the houses, and at that time already also starting gas coming into several houses. So our biggest concern was the health of the people in the village, and for that we wanted to take away the source as quick as possible. That was our main objective.
Mm-hmm. And we're looking at a plume here. I'm sorry, there's not a scale, but on some of the other photos, you'll see a rail line which goes here, right? And you'll see the river is over here. Roughly, how far is this? Is this like 1 kilometer or 2 kilometers?
Yeah, about 2 kilometers.
2 kilometers. So about a mile long, pretty strong plume. You know, yellow is 2,000 to 5,000 milligram. Is this micrograms per liter? Anyway, it's
Micrograms, yes.
Micrograms per liter. So we're talking about treating the source area right here, right, and then having an impact on this plume some years later.
Yeah, correct.
And what are the indoor vapor issues?
Yes, well, of course, it's PCE. The hazard risks are known, carcinogenic. So we had to install at several houses a vapor control system, ventilation system.
Okay, and of course, that's something you would like to stop as soon as possible by making this plume much smaller and less strong, I would assume. All right, Marco, would you mind explaining the options for treatment that was considered?
Yes, I don't know if you show the next slide then, yes or no? Yeah.
Yeah.
Yes, so the original solution, let's start with that, was to take out an oil spot of the site of Kaldik, and also to start a soil vapor extraction system in the unsaturated zone. So that's also how I learned to know, how I got to know the site, because as HMVT we took care of those two issues. And then next step for Kaldik was also to treat the groundwater below the groundwater level. And the initial idea was to install, let's say, a never-ending hydraulical barrier and to contain the hotspot on their own side, so to say, so that it did not spread anymore underneath the village and towards the river. And the idea was to pump 85 cubic meters an hour to treat that water and to re-infiltrate again. And at that point, because I got to learn to know the site, we got in touch and discussed with Henk, hey, perhaps there is a more smarter solution, so to say, for the groundwater. And then we came up with, why not take out the source zone and do it in such a way that there is no leakage anymore towards the plume in the future. And then ERH was selected.
Okay. That isn't, but isn't ERH always more expensive than pump and treat? Maybe I should ask Henk that question. And Henk, when you answer, would you please hold your microphone closer to your mouth, because some other people cannot hear you very well.
Yeah.
And
Yes, I will.
Okay, thank you so much.
I will go on. Yes. Well, when we started to look at the remediation, as I just told you, our biggest concern was the total time. And when you start with a pump and treat system, you know you are busy for 20, 25 years or even more. And then also taking into account the number of costs, you will get a huge amount of money. And when calculating the cost of ERH, well, it turned out to be much cheaper. And also then in 2 months you were ready. And that was our goal. We wanted to be to remove the source zone as quick as possible. And then of course the financial benefit.
So the pump and treat system is cheaper to install, right? But the problem is you can never turn it off. So the costs keep going up. Is that right?
That is correct. You have some direct costs, of course, that are much higher. But when you take the total of the remediation, ERH is cheaper.
Okay, thank you. And Marco, I'm sorry, I will just want to go back to the design, if you don't mind explaining the ERH design then.
Yeah, I will do that. I might like to add that I think also benefit for colleague Henk was that the site was already abandoned. It's now remediated, so to say, and it's also now more suitable for redevelopment as well. Mm-hmm. But anyway, the ERH design, yes, it was very flexible, so to say, because when we start looking at the site, we knew there was a hot spot with DNAPL, but the complete delineation of the DNAPL was not good yet, so to say. So we started with our first design with a 400 square meter treatment zone area, so to say. But we also said to the consultant, Antea Group, as well as Caldic, please do some extra delineation, because we're not sure if we treat the complete DNAPL zone. And that's one of the things you need to do, otherwise you still end up with a plume. And then in a few months' time, the delineation was done. And we started to install electrodes. But also during the installment of the electrodes, we took also soil and groundwater samples to double check the delineation. That was a very wise thing to do, because during installment, we found out we also had to go a little bit further towards the railroad track, and also some bulbs to the right side of this picture. Yeah. Yes, over there. That still needed some additional treatment, so to say. And in the end, we end up with a treatment zone of about 1,100 square meters, and one deeper hotspot in the middle. Yeah.
Let's talk about the hydraulic control system. You know, essentially the topic is here how to slow down the groundwater, right? So that thermal can be effective, if you don't mind.
Yeah. Yeah, sure. Actually, the modeling of this was done by Antea Group, the consultant of the project. And basically, the design was such that 4 extraction wells were installed, not really upstream of the source zone, but a bit to the side. Those those red spots, so to say, yes, over there. The groundwater was extracted over there and then infiltrated downstream of the treatment zone with a drain system, so to say, a shallow drain system that was installed. And the extracted flow rate started with 25 cubic meters an hour. And before infiltration, the groundwater was cleaned as well by activated carbon. So, and that worked quite well. We did, of course, measurements to see if the groundwater flow rate stopped, and it seemed all okay. Then we started with the ERH. Yeah.
So these little red lines are the flow paths for water muddled. So water would come towards the site and then turn and get extracted. And it should be standing still in the middle, and then it's pumped out here and then injected back into this trench, and then it runs. So it's basically pumped around the source area. That was the trick. Okay.
Yeah, correct. Yeah.
All right. Now we want to show you everyone a little bit, just an impression of what the site looked like, and feel free to explain, either of you, what you're looking at, please.
I'll try to do that. You can see here the treatment zone with the soil vapor extraction lines to capture the vapors, of course, we created. The cabling was buried below grade. And what you can also see here is the step down. This is one of the step down trafos we use to lower the voltage. And the big, oh, sorry, it goes very fast. Of course, we do always measurements to see it's safe on voltage and so on.
Okay, yeah.
That's what we are doing here, checking that it's safe to enter the site, so to say. I think a thermal remediation project goes on 24/7, and it is very important that it will keep running, so to say. So we check all the time if it goes well and according to plan. And this is how the site looked like from an aerial view.
That's the source area, and behind here, the river Seine is over here, right? And these are some of the houses. Yeah.
Actually, the river is on the other side, but
okay, sorry. Okay.
But on the back here, the railroad track is perhaps seen. Yeah.
Okay.
Yeah.
Okay.
And maybe on the left here, the gray box, so to say, that's the power control unit we use. Yeah.
Thank you so much. See if I can figure out how to move to the next slide, and then we can go into the results, if you don't mind, starting with the temperatures that were achieved.
Yes, sure. Of course, in situ thermal treatment is all about achieving the right temperature level. And in our case, it's towards boiling temperatures of water, of course. As you can see, we started in, it's very small for me, but somewhere in spring, I think 2017, this started. Once we start, you can see the temperature rising in the different sensors we have installed to monitor, and that goes up about 1.5 to degrees per day. And then eventually we want to reach boiling temperatures. So for this side, the average temperature we achieved was about 105 degrees centigrades. And in total, we heated about 4 months, in total. As you can perhaps also see, we have here one sensor that stayed behind a little bit. That was also because we, during the project, we did have some problems with the hydraulic control. So we had to adjust that system as well. But eventually we were able to succeed, so to say. Yeah.
All right.
Yeah. So maybe, I'll continue or Gorm?
Yeah.
Okay.
Explain what the trouble was with the hydraulic control, please.
Yes. What we did see during the project is that, especially in some let's say, shallow temperature sensors, as well as some deeper ones. That's actually the picture on the right. You see the temperature of shallow sensors is staying behind. Then when you go deeper, it goes to boiling temperatures. And then in the deeper sensor is also not heating up quite well. And what we found out is that probably we extracted groundwater, as you know, and we infiltrated water shallowly, that the infiltration of let's say cold water close to the treatment zone shallowly flowed back into the treatment zone. So what we first did is to reduce the pumping rate of the barrier system from 28 to 6 cubic meters an hour. And then also the shallow temperatures improved. But also, if you can go perhaps to the next step, we also saw that the deep temperatures did not improve by doing so. What we did to overcome that problem was to install 2 extra extraction wells upstream of the treatment zone, and 2 extra infiltration wells indeed downstream of the treatment zone, and to extract and infiltrate about 5 cubic meters of water extra, especially in the deeper layers. So these wells and infiltration wells did have deep screening because groundwater was actually still flowing too fast in the deeper zone, so to say, during the project. And once we did that, the problem was quite quickly solved, and temperatures were okay, and the project was completed, so to say. Yeah.
So that's what we see down here. The blue line comes up to the same temperature as the other ones. And for those who can't see, I'm sorry about this, but this starts in May and it ends in the end of September. So we're talking about a 4-month period, and about halfway through you found this issue and you modified it with the 4 additional wells, and then the temperatures responded. So it's interesting, right, that really the best way of understanding where the water is flowing and whether it is a problem is actually to look at the temperatures. If you know you put in enough energy that it should get hot, but it doesn't, that's the best tracer you have, is to look at the temperature probes. And not just have a few, but have many and have them over depth in a lot of discrete intervals. You can find out these things.
Yes.
Awesome. How much mass came out, and how did you know that it was time to turn it off at the end?
Now, of course, first the temperature profile should be in should be okay, so to say. But we took groundwater samples during the project. Also, we took soil samples during the project. But in the end, we also took, of course, final soil and groundwater samples. So taking samples, that's how we check. We check temperature profiles, but we also checked what concentration levels do we have in our vapor stream, so to say. And that's also the graph you see over here. And when we start, you can see the orange line, so to say, are the PID readings, or milligram per cubic meter, probably over here.
Yeah, they're actually calculated to be kilograms per day of PCE removed based on the PID results. So
whatever, it gives the same profile, so to say. Huh?
Yeah.
And so when we start, the influent concentrations, of course, are low, but during the project, when it starts to heating up, mass is evaporated, and we see it in our influent, and that goes to a peak and goes then back to very low concentration levels. And that's also an indication that everything is boiled out, so to say.
Mm-hmm. Very good. And I
Three line.
very good. In a few minutes, we will have questions from you guys. I should have said that in the beginning, but if you have a question, you can type it into the Q&A area on top. There's already about 10 questions in there. I'll ask Henk one more question, and then we will go to the Q&A. So please don't be shy. Type in questions for us, please. Henk, did it work? And what is the plume look? What is the plume like today?
Yes, it really did work, and well, the site now today is again full with green grass again. But of course, I think you mean the pollution. Well, well, we removed the source. There was no rebound. Today, under most houses, is reduced less than 500 micrograms per liter, where it was 100,000 or more before we started. So a tremendous good result, and that in less than 4 years. And even the situation is now better than the ground model estimations showed, which were made before we started. Well, maybe one remark, as Marco mentioned already. Well, the site is again ready for industrial use again. So activities can be started. Well, at that time in 2017, also for the French authorities, ERH was a pretty new technique. And well, when we after 4 months went to the town hall and just told them we are ready, well, there was some unbelief, and they were a little reserved. So they waited with the permission to stop the barrier, and that took more than a year. And then after that year, also the barrier was stopped.
Thank you so much. I think I will start asking some of the questions that have been typed in. One of them is from Mike Kavanaugh. He's saying, what was the release? What was released? Another person is asking, the plume on the left here seems wider than you would typically expect, and I guess that refers to that blue halo around, you know, the orange. Do we have any explanation? First, you know, how did the release of PCE occur? Secondly, why do we think the plume is this wide?
To come to the first question, how did the PCE in the ground? Well, on site also there was a railroad track many years ago, and the PCE was transported by the railway on site, and then on site it was filled in cans, drums, etc. Those drums, cans were transported to the customers, but the customers returned it again, and returnable packaging is never empty. So what happened on site, they turned the packaging upside down, waited everything to get out, and then refilled again. And that's why the PCE was in the soil at the end. So the method of working at that time, and then we speak of course of 50 years ago.
Yeah. And for the second part of the question, which is why is the plume so wide? I don't know, Marco, if you have an explanation, but I've seen.
I do.
Okay.
Yes. Yeah. If you look at the left picture, there is something very small called RSZ2, I think. But there was a small, let's say, source zone on the southern end of the caldic side.
Yeah, here.
But not a very major one. And that one was also remediated by soil vapor extraction, I know. But it was not very major one. So the major hotspot was in the center of the caldic side, so to say.
And just the way the graphic is, it could also be that these are actual real groundwater samples, but if there are not that many sampling wells, maybe the computer takes liberties to interpolate between points, right? Maybe
Yeah.
it's 0 out here and 100 here, and then the computer thinks there's something in between. It may not be this wide. At other sites, it can be seasonal variations in rainwater and actually flow direction. As you can see, even at simple sites like Borden up there, very simple sandy site, actually the direction of water flow can change some degrees, and that could also make the plume wider sometimes.
Yeah.
If anyone, I don't know, Marco or Henk, if you're reading the questions, feel free to pick one and answer it if you like.
Oh, sorry, I have not done so.
The next one is from Eric, and he basically is asking, how did you estimate the groundwater flow in situ? How did you come to estimate? I think we said your slide had 10 meter per day, one of the early ones. How was that estimated?
That was that was being calculated and measured already since many years when we came along by the consultant. They also installed and produced these graphs, so to say. They were already investigating the site, of course, and delineating it, measuring water levels and so on. And
yeah,
so that's how it was measured. Yeah. Okay.
Eric also asked, why didn't you use steam instead? Why didn't you choose steam enhanced extraction? That's a very good question. I admit you may have to go back and explain the stratigraphy, how it was both clay on top of relatively tight chalk and then more permeable chalk.
Well, perhaps a good question. And also you can help me out here perhaps as well, Gorm. I think back then at that time, it was not in our, let's say, scope or in our mind that was perhaps an option as well. Mm-hmm. Nowadays, especially TOS also does do much more steam and conductive heating projects, so to say, and then there is the possibility to combine. But at that time, ERH was our main treatment system, and we decided to do it only with ERH.
Yeah. I think that's a good, honest answer. Another way of answering it is, remember the sequence we had. There's a thick layer of clay up above the chalk, and there's also some mass in the clay, and especially the bottom of that layer. And if we were only injecting steam, it would probably work just fine for the deeper portion where the permeability is high. But we have to remember it's still chalk, so it is still a fractured rock. It's not a necessarily very predictable where the steam will migrate if you inject it. And I think maybe 20 years ago we would have probably started with steam if you had asked steam tech at the time, company living by doing steam. Nowadays, when you have very tight clay and you have a transition and there's uncertainty as to the permeability and the flow, it can be more predictable to use electrical resistance heating or thermal conduction heating and then stop the water flow, right? That kind of makes everything easier and simpler. You don't rely on permeability and flow paths as when you're injecting steam.
Mm-hmm. Yeah.
So there's a tendency over the years to use more of the electrical methods and steam to support them when necessary. It could, for instance, also have been a solution of ERH and TCH in the bottom of the clay and then steam in the more permeable chalk below. That is also a possibility. And I think for each site, we simply look at that and we calculate which solution costs less, and then we choose that one.
Yeah. Okay. Perhaps you best guide us through the questions, Gorm.
Yes, I will. There's a few more. One of them is essentially, did you consider doing injections and amendments, or maybe a passive reactive barrier instead?
You mean for treatment of the site as a whole, so to say, instead of ERH over a hydraulic barrier?
Yeah. I didn't ask the question. It's me here has typed in the question, so I'm not quite sure, but I think one of the answers is there was so much mass here, DNAPL, right, that it was not really, in our mind, realistic to try injections. Injections are typically either for bioremediation or for in situ chemical oxidation or in situ chemical reduction. But if you have 6.5 tons of PCE DNAPL, that will probably mean that you have to inject many times before you see any significant reduction in the mass.
Yeah, I can add to that. I know that that by Antair Group, they made a remediation plan, viewed all kind of options, and selected, let's say, the geo barrier. Back then, ERH was not on their horizon, so to say. But what I do know from this side, because I also looked at, are there smarter options possible, so to say. If you use chemical oxidation in chalk, you will have a very intense reaction. Eh? It's not feasible, so to say, for instance. Yeah.
And there's a very good question, maybe we forgot to say, but someone is saying, so you pump out water and then you re-inject it downstream. Doesn't that just spread the contamination? In other words, did you treat the water that was pumped out before it was re-injected?
Yes, that's also one of the reasons to install the extraction wells away from the hotspot, so to say. So soil, a clean groundwater that flowed in was extracted, but yes, it still was treated by activated carbon before re-infiltration.
Okay, good. So
yeah. And the same counts for the additional wells we installed when we saw some heating problems in the deep layer. That water was also cleaned before re-infiltration, of course.
Yeah. One of an anonymous person is asking whether there is anything written up about this, like a paper or something that's available.
Yeah, I believe there is.
Okay.
But if you want to have one, we can send it. Yeah.
Yeah. The other thing I should have said in the beginning is this webinar is recorded and will be available also to watch again. And you can always send us questions or requests. I think when you're also, we will go through all these questions. I know I'm not going to be able to remember all of them and I'm going to miss a few. Send us an email and complain, or we will try to answer them in writing to those who have not had a reply during this webinar. There is one quick question about the mass removal. There was, when we looked at that curve in August, there was a spike in the mass removal rate. And why is that? What do you attribute that to? I think we're talking about this little spike down here.
That's a good question. I think that was caused by the installment of the additional 2 deep extraction wells and the infiltration wells. Once we did that, also the lower treatment zones got hot enough, and also that mass came out in the end. But yeah, it was only a little spike locally, of course.
Yeah. Yeah, it would kind of make sense when you look at the temperature that was lagging at the bottom, and it came back up in the beginning of August right here, and that's the same time that you received a little more PCE in the system.
Yeah.
So
I believe that was it. Yeah,
it's reasonably logical. It's not always connected like that. Sometimes there's other things happening, but that could definitely be why.
Mhm.
Yeah, David is asking, from Arcadis is asking whether you considered thermal conduction heating at the time, and if you did, why did you not use that and ERH instead?
Well, I would say we did not. TRS and TRS Europe focused on ERH back then. But I think if you look at the site now and if you see how much water is flowing and how deep it had to go, I think that, but you can explain perhaps much better than I can do, Gorm, but with conductive heating, you also have to remove all that water from the subsurface and evaporate it more or less.
Yeah, I think
and
maybe,
that would be difficult.
yeah, maybe a very straight and an honest answer to it is if I was Terratherm, I would have probably said thermal conduction heating. If I was TRS, I would have said ERH at the time, honestly, because that's the technology you're best at, implementing. Now, having worked with steam, TCH, and ERH for a while, I do think that for sites where the water flow is a little on the high side, little more than you are comfortable with, and you have to do something about it, such as a barrier or pumping and re-injecting. I have learned that with electrical resistance heating, because when it's wet, it's easy to inject electricity. ERH is a little more robust when it comes to water presence and flow. So areas that have a little more water flow, you can increase the flux of energy, and you can heat water moving faster with electrical resistance heating than you can with thermal conduction heating. Thermal conduction heating has other strengths, of course, such as if it's super tight, everything works really, really well. If you have to go to higher temperatures, if you're treating PFAS or PAHs, you have to use thermal conduction heating. So it's not one technology is better than the others, but for water flowing and potentially cooling a zone, ERH can be a little more robust, or quite a bit more robust.
Okay.
Final question before we stop. What technique did you use to treat the vapors? How did you treat the vapors coming out?
Oh yes, I can answer that. I quite easily we treated the vapors with activated carbon. We checked, of course, up front what would be the most economical and best solution technically, and with those masses coming out, still activated carbon was economically the best solution, so to say. An alternative could have been an oxidizer or something like that, but you always have to take care with chlorinated solvents and oxidizers. It's quite complex. Yeah, so GAC. And I think the benefit of using GAC for this site like this is that we also see very, very robust absorption rate, so to say. I don't know exactly anymore for this site, but let's say 30% or 35% or something like that, or even higher at some points.
Yeah. And maybe I'll sneak in one last question. After thermal treatment, the groundwater concentrations, how high were they actually? I guess we can look at these maps and see, at least 4 years later, we are light blue where the source area was, right? So we're talking 50 to 100 micrograms per liter of PCE now, where the source used to be. But I think there was some data shown that indicated quite a lot higher concentrations right at the end of thermal. Is that correct?
Yeah, right at the end of thermal, the average concentrations were about 14,000, if I remember correctly.
Yeah.
But main goal was to get out the DNAPL and to achieve low, let's say, soil concentrations. What I've learned from Henk, because we stayed in touch, of course, on this side, is that a year or so later, concentrations already dropped towards a couple of thousand, and that still continues. And as you see, they are going further down over time as well.
Yeah. Okay, thank you so much, Henk and Marco. And thank you for everybody who listened. We will be back with another webinar in a month or two. Thank you.
Thank you, Gorm.
You're welcome.
Bye.